All right, you'll have time to finish up the survey a little later. You can turn those before you leave. Those in before you leave class today. But the quizzes, we're going to have a total of maybe 25 points. So we'll have a number of these. They're going to typically be short, like 1 minute or 10 minutes at the most. Except the quiz schedule isn't in the syllabus. If you take a look at the syllabus, see the exam schedule's there, but the quizzes aren't. And so normally I look at this by week. So this is the first week, second week, but I screwed up the dates here. So I was working on this and it updated. The computer restarted, but I didn't save the file. So I'll fix that and then post it on Piazza again. I'll make a copy of it. But the weeks are accurate though. So the first week we're still continuing with chapter 2 here. We'll probably start chapter 3. And so the quizzes are going to be spread out over the semester. It's not worth that many points. When we look at the points, we should end this course with a total number of points of around 875. Depends on how many quizzes we have and other factors, but around 875 points. Most of the points are going to be in the exams. So we're going to have 4 midterm exams we talked about yesterday. Those are going to be 100 points each, or 400, which is about half your score. Then we're going to have the final exam. It's going to be 175 points. I know, just about 20% of your grade. Homework assignments. We'll start assigning those. We're going to do paper homework assignments this semester. There's also an online homework package that comes with the book. It's called OWL. But you don't have to get that. Labs are worth 180 points, roughly 20% of the grade. Now, there's a strange thing about the labs here. At UCLA and Cal State, the lab course is a separate course entirely. And so, for example, at UCLA, the lab course would be 1 unit, the lecture course would be 3 units. And they're totally separate grades, so you could end up failing, failing lab, and passing the lecture part. And so if you fail lab, you have to repeat the lab, or vice versa. You can end up passing the lab, but failing the lecture, so you'd have to repeat the lecture. But here, the lab and lecture are combined. And since the lab and lecture are combined, we have an agreement with UC system. That is, the agreement states that since it is possible to fail the lab and still pass the course, they find it unacceptable. You know, if you fail the lab, they want you to repeat the lab, right? And so based on the number of points, I mean, if you lost all the points, let's say you got 0 points in lab, then you still could theoretically end up with a B in the course. Well, that's not acceptable to UC. So what they said is that if you do not pass the lab portion of this course, that is, if you don't get a certain number of minimum points, which isn't that much, 55% of the lab points, then you aren't going to pass the course, no matter how well you're doing in lecture. You're going to have to repeat the entire course, basically. And so that's how it works here. And so lab attendance and lab participation is mandatory, even though you might not think it's that many points, and you can sacrifice a lot of the points you can. In fact, excessive absences from lab will result in you being dropped from the course. You know, even if you have a passing grade in the course, I still have to drop. All right, the quizzes though, this is just 1 point out of 875, so it's not big. And I'm not going to grade these two strictly. And so what do scientists do? Scientists, you know, you want to put it in your own words. Like, for example, yesterday we had the lecture on it, and then you want to think, you know, how would you describe what a scientist does, you know, rather than what I said. What did I say? They observe nature. Right. What they want to do is they want to understand how nature works. Right? They want to see how nature works, and how do you figure out how nature works? You observe nature, right? Look for patterns. It's good. But what you want to do is you want to put it in your own words, right? And the same thing with chemists. What do chemists do? They study matter. Or you can be a little bit more specific. They study what about matter? They study the physical and chemical properties, composition, and structure of matter. All right, and so we'll take a look at those. All right, that's a quiz. This is a point breakdown. Now, a lecture point and a lab point are the same, and the quiz point and exam point are the same. So 1 point is 1 point. And basically, they're not weighted differently. They're all weighted the same. Basically, you'll need 90% of the points to get to 8. Sometimes this drops a little bit to 88%. It depends on how hard the exams are. 80% and above will be guaranteed B. 65% and above will be a C. This order doesn't change. The 80 might drop a little bit, but this is already a widespread. A lot of classes at UC, it'll be 70% above. All right, on the survey forms that you have out there, if there's any special requirements that you have, or you need assistance, additional assistance in any way, let me know. We also have a special resources center that can help with test taking and whatnot. So either contact them or leave a note for me. Okay, if there are any changes to this schedule, I'll try to announce those in class or on the outside. All right, and cheating, of course, cheating's not allowed. Any cheating will be reported to the dean of student affairs. Academic honesty is mandatory. Before you get to this stage, look for getting help. You can get help from maybe asking fellow students or me on Piazza. I'll try to answer any questions you have. There's also free chemistry tutoring available in the library. I haven't received the hours yet, but pretty soon they should post those. The MESA program is good as well. You can go and apply for the MESA program. Once you're in the MESA program, they have a free facilitator-led study group. This study group is good because there's no financial or time obligation. On the internet, there's Khan Academy, which has a lot of videos. Study.com has a lot of videos to watch. We have a little room over here called the Chem Study Room. As you walk into the corridor, the main chemistry building, it's the first door on the left. They have some tables set up for studying, but they also have a small bookshelf. On that small bookshelf, there's some alternate texts. Also consult if you're confused about a certain topic in our textbook or something we discussed in class. There's one other thing, and that's the office hours. If you could let me know, if there's a specific time that works well. What I was thinking, as far as office hours go, here's the space is before class, a little bit before class. Then I can stay after class for a little bit as well. But if there's a particular request for office, like half hour, 15 minutes, let me know what a good time is. I'll try to fit that in. chemists study matter. You know, they call it substances in the dictionary definition, but basically chemists study matter. What is matter? Matter is anything that has mass and occupies space. So it's what we call the physical material of the universe. Physical material being something you can, touch, either with your hands or with a probe, whatever. You don't necessarily have to see it. Can you see air? No, air is invisible, but you can probe air. Wave your hand back and forth, and you can feel it. Right? So that takes up space. And then we were talking about vacuum. I think this is where we left off. Is that where we left off last time? Now, is a vacuum matter? No, vacuum is not matter. It's where you take a container and suck all the matter out of it, so there's nothing left inside, except the container walls. The container walls would be matter. But vacuum is not considered matter. How about light? Is light considered matter? No, light is not considered matter either. Light is considered energy. Right? All right, when we observe matter, sometimes you can see it, sometimes you can't. But let's say we can see it. When we observe matter, we can observe it at different levels. For example, at the macroscopic level, we could just observe it with our eyes. But sometimes the matter is too small to observe with our eye. So, for example, a piece of copper, in a copper penny, we could observe that with our eye. That's macroscopic. But eventually, if we break that piece of copper down into smaller and smaller pieces, pretty soon it'll go invisible. It's still there, we just can't see it because the particles are so small. We would need a microscope to see it. If we need a microscope to see the tiny particles of copper, then we call them microscopic. If we continue to break it down even smaller, pretty soon the microscope can't even detect it because the particles are so small. In fact, what's the smallest piece of copper that we can have? An atom of copper. And so if we just keep breaking it down, pretty soon we'll be left with a single atom. And with a single atom, we would need specialized equipment. Can you name something that might be able to see or detect atoms, single atoms? In fact, have you seen an atom? Has anyone seen an atom? I learned about atoms, I think in 7th grade. I learned about atoms. And I just assumed it's true because, atoms must exist. My science teacher says they exist. I just believe that. But that's not really the scientific method. You shouldn't just say, okay, believe that. What you want is some kind of proof that atoms exist. You want some kind of evidence. So if somebody were to ask you, I'm not in the atoms camp. I believe that if you take a piece of copper, you can make it smaller and smaller until, with no end. You can make infinitely small, an infinitely small piece of copper. But, if you're in the atoms camp, you say, no, you cannot make it infinitely small. Eventually you're going to hit a point. What point is that? How big is that? So that's something we should maybe keep in mind, how big that is. You know about how big atoms are? This is a size scale for macroscopic objects. Objects that's like 1 meter. That's 1 meter. That's like 3 feet. We'd have no problem detecting it. All right, so if it's 1 meter big, a couple meters. Here's this person. Sheet of paper. see. Wedding ring, easy to see. You know, but as we get smaller and smaller, eventually we get into this range where, you know, it's not like this is a meter. This is what we call a decimeter, which is a tenth of a meter. This is a centimeter, which we'll call a hundredth of a meter. This is a millimeter, a thousandth of a meter. What's this? Micro, a micrometer, or millionth of a meter. You know, so if you take 1 meter, which is this, and divide it into a million pieces, each of those pieces would be a micrometer. And so once we get into things on the order of micrometers, we're going to need a microscope to observe those. So like plant cells, animal cells, bacteria cells here on the order of micrometers or microns. Okay, then you can see the yellow start to fade and we go to green. You know, these are getting too small to see. So individual viruses, can you see those with a microscope? No. We'll need something better than a microscope. What would be better than a microscope? Well, a microscope that doesn't use regular light, maybe a microscope that uses electrons instead. Well, we'll talk about electrons later. So electron microscope. Or maybe a scanning tunneling microscope, then we can see these things here. And then we get smaller and smaller until we hit the atoms. So about how big are atoms? You know, atoms are the smallest piece because, you know, the smallest piece of copper I can get is a single atom. A single atom would, like a single atom of copper would look like a little ball-shaped particle, like this, a sphere. And so about how big are atoms? Well, this is micro. Do you know what N stands for? Nano. Nano, and P stands for pico. And so atoms are on the order of picometers in diameter. And so what are the typical ranges in terms of picometers? The typical range in picometers is about 100, even though it doesn't look like it. It's about 100 to about 600 picometers in diameter. Measuring the diameter of atoms is tricky because, as our book says, this thing comes directly from Caracolici, is trying to measure the diameter of an atom. You take a probe, and then you hit the surface of the atom. When you hit the surface of the atom, is it like this? No. They say trying to measure the surface of an atom is like trying to measure the surface of a rotten grapefruit. This is Caraccolici's words, I think. Using a needle. And so if you're trying to measure the rotten grape, in other words, it's like a cloud. It's a fog or a cloud. So you're trying to measure the edge of the cloud. It's kind of hard because it just kind of thins out. Do you see that? And so it's a bit tricky. So what they do is they just measure it to a certain force and then they'll call that the surface. But it's not really a surface like this. You know, it's a surface like this where you can penetrate the surface. And so atoms, you'll see different sizes, especially depending on how it's bonded. We have different sizes of the atoms. You know, is everybody familiar with the periodic table? The periodic table, we have lots of different atoms on the periodic table. Let's take a look at the periodic table here. Not that one. These are all the types of atoms that we can have. You know, there are lots of different types of atoms. This would be like, you know, when we're looking at dogs, there are lots of different types of dogs, right? We have some big dogs, some small dogs, you know. And so what are the small atoms here and what are the big atoms? Do you know? Do you know which one's the smallest atom? You know, not all these are the same. Yeah, you'd think hydrogen, but that's a really good guess. I would guess hydrogen too, but it's not the smallest. Which one would you say is the smallest? Helium. Yeah. Helium is the smallest atom. And so helium would be like less than 100 picometers in diameter. It's like this. What's the biggest atom? What do you think? So the helium atoms are kind of small. The biggest atoms would be here? Okay. Let's see some pointing down here, like radon or xenon or this. Yeah, these would be a lot bigger than helium. So helium's like this. These atoms are going to be a lot bigger, but these aren't the biggest. Yeah. What are the biggest atoms? The biggest atoms on the periodic table are actually here. What the biggest atoms are. FR, do you know what FR stands for? This is the symbol for francium. Francium's big, it's a big atom, but francium's also radioactive. And radioactivity is that there are some atoms that are inherently unstable, and these atoms actually end up breaking apart, forming different atoms. And so francium we don't deal too much with. Instead, we deal much more with cesium. Cesium has the symbol CS, capital CS. Cesium is a very large atom. It's the biggest atom, it's the smallest atoms. And so what we want to do is we want to understand the atoms, not just in terms of properties. That would be a property. Would that be a chemical property or physical property? That would be a physical property. It's physical size, you know. Then we want to know how they behave. You know. How they behave is helium. When we think about helium, is helium like the vicious dogs of the dog kingdom, or is it really mellow? Helium's very mellow. Yeah. However, cesium's not. Cesium's not so mellow. So we'll learn more about that. We want to figure some things out. So sometimes it's easy to just visualize these using charts like this. Here you can see. Smallest atom here, helium. How big is it? It's less than 100 picometers. Biggest atom down here is like cesium, like 600 picometers, something like that. 100 to 600 picometers. So pico is very small. A picometer is this. You know, a micrometer is if you take a meter and divide it into a million pieces, each one would be a micrometer. But if you take this meter stick and divided it into billion pieces, what would that be? That would not be a pico. Do you know what it would be? A nano. So if we took this and sliced it into a billion slices, each slice would have the thickness of a nanometer. A picometer, we'd have to take this meter stick and slice it into a trillion slices. If we put a trillion slices in there, then we get a picometer. And 100 of those picometers would be about the size of an atom. There's another unit that's very handy for measuring the size of atoms, and this is something I had to memorize when I was a student. And that's this, an angstrom. An angstrom is 1 times 10 to the minus 10 meters. 1 times 10 to the minus 10 meters is 100 picometers. That would be an angstrom. So if 1 angstrom is 100 picometers, then atoms range in diameter from about 1 angstrom to 6 angstroms. 1 to 6 angstroms. But people don't like angstroms as much anymore. And it's a very simple reason why people don't like angstroms. If you use angstroms, let's say the diameter is 150 picometers. In angstroms, it would be 1.50 angstroms. Adding that decimal point there makes the number longer. So a lot of people don't like writing decimal points there. So they'll do things in terms of 100. All right, so these are the atoms, but you might say, or somebody might ask you, you know, what's your proof? You I have these nice cartoons of atoms, different colors. Those colors aren't accurate, but prove to me that atoms exist. That's typically what happens in science, because science, there's a natural skepticism to science. It's called peer review, and this is how science kind of, it's like we have tests. In chemistry, unfortunately, we got to have the tests, the midterms. I know I hate tests too. I really don't like taking tests. But you're always tested in science, no matter what. After I finished all my classes, I'm still tested. I'm still tested because, if I do some research, I have to send it out for peer review. Peer review. And I have to go through the whole peer review process. The peer review process is you send it out to like 3 experts in the field, and then they check your work, basically. And essentially, they're just grading your work. Is it good enough? Some of the harshest peer reviewers, or the hardest, or the ones with the highest standard, belong to some of the prestigious journals like Nature, or Science magazine. Those are very prestigious journals, and those are very difficult to get into. At least get your work published in there. But it runs the whole gamut. Now, there are places where there's no peer review process. If there's no peer review, what we call referees looking at your work, then you can publish anything. And if that's the case, then nobody's going to hold much value in it, because nobody's checked your work. So that's the problem. And so scientists are always looking for peer-reviewed work published in respectable peer-reviewed journals. But oftentimes the question will come up. You make the assumption, and I made the assumption. Why do atoms exist? Because ever since 7th grade, I've been told atoms exist, right? Ever since 7th grade, I've been told atoms exist. But is that a strong argument, or is that strong proof that atoms do exist indeed? No. So can you give me a better argument for the existence of atoms? Now you have to think about when this theory came about. This theory came about in the 1800s. And the person who proposed it is a guy named Dalton. And so there are people who are in different camps. There are people who are in the atoms camp, and there are people who are in the infinitely divisible material camp. Eventually the atoms camp won over the majority of scientists. How come? How come you should believe in atoms? So this is part of the scientific method, and this is the way we got to start thinking about things. We want to be able to justify the existence of atoms. And so in the 1800s, did they have electron microscopes in the 1800s? Did they have scan and tunneling microscopes? There's another way to see atoms. Do you know another way to see atoms? Did I mention this? X-rays? Did I talk about this? Nowadays, it's not a problem to see atoms because you can see atoms using X-rays, scan, tunneling, microscopes, etc. This is the image that you get from X-rays. You do is you shine X-rays on there. This is spread out. There are no sticks there. This is just spread out to show, how things are attached to each other. See that? When you look at these atoms, do these atoms look spherical to you? A little bit, but they kind of look oval in shape. Do you see that? And so if that's the image from X-rays, then maybe atoms are oval in shape, not spherical in shape. Well, look at that. That doesn't look so spherical. This one kind of. That is kind of oval in shape. So maybe I need to rethink it. Maybe atoms are not spherical. Maybe atoms are oval. it turns out I don't need to rethink it because it's the process. You know, when they image the atoms using X-rays, it takes a lot of time because what they do is they shine X-rays at the atoms, in this case at the molecule. This would be a molecule. Molecule would be a collection of atoms that are bonded together to form a discrete unit like this. They shine X-rays at this, and then the X-rays are scattered off the atoms, and then they collect all the scattered X-rays and rebuild that into an image. You know, and the reason it takes so long is because there's no lens for X-rays. You know, if we shine visible light on this object, then the light is scattered off. This hits our eyes. It's refocused into an image. We have a lens in our eye that can do this. If there's an equivalent lens for X-rays, then we could hold that lens and actually see the atoms. You know, wouldn't that be weird? Since it takes a long time to rebuild that image, what you're seeing here is the movement. The atoms aren't fixed in position. In fact, at room temperature, the atoms are moving a little bit. And based on that movement, you're seeing a blurred image of the atom because it's moving back and forth a little bit. And so that's what causes it to be oval in shape here rather than round. If we're to freeze those atoms in place, then we'd see this, more like this. Okay, the atoms are color-coded here so you can see the differences. The greens would be carbons here. The blues would be nitrogens, the reds are oxygens, and the whites are hydrogen atoms. These are just different atoms. All right, so do you have the proof for me that, you know, if you think about in Dalton's time, what proof did he have? In our time, we have plenty of proof. You know, there's no disputing atoms now. That's probably why people don't offer that much proof. The reason that, because people can see individual atoms using X-rays, although hydrogen atoms are hard to see. But we can see those using neutrons pretty easily. Or you could see individual atoms using a scanning tunneling microscope. Not only can you see individual atoms, but you can manipulate single atoms as well. So let's take a look at that. Here. Xenon atoms are kind of big. These are individual atoms that scientists at IBM arranged to spell IBM by atom. And so here they're just moving the atoms on a surface like that. The atoms, they look like Hershey's Kisses. It's just because of the way the probe is, the way the probe acts. Do that, but when we look at surfaces, it will be round, spherical. But these are individual xenon atoms here, spelled out. And so they can manipulate these atoms one by one. Have you heard of the Xenon Man? No? That's not the Xenon. That's not the Xenon Man. Which one is the Xenon Man, A, B, or C? C. This is the Xenon Man. This is the IBM people built this also. This is individual atoms of xenon put together to make this little man. And so they can manipulate these atoms. This is a very cold surface. That way you don't. Do you see that vibration? The kind of the oval shape or something? No. How do you get rid of that vibration? They chill it down. The colder and colder it gets, the less the atoms move. The hotter it gets, the more the atoms move. So if they warm this up, the atoms are going to be. In fact, if they warm this up too much, the atoms are just going to be all over the place. They really have to cool it down to get the atoms to stay in place. Freeze them kind of in place. Now, how do we know that atoms, you can't just break the atoms into smaller pieces? So if I take one of those xenon atoms and then smash it, will I get a whole bunch of little xenon atoms? Like mini atoms? No. No, because nowadays we have, super colliders. You know super colliders? Super atom smashers. They can accelerate these atoms and smash them into one another or into some target. In fact, they have a huge one in Switzerland called the Large Hadron Collider. Have you heard of that one? It's been getting a lot of news lately. It's giving a lot of insight into the theory and experiment observations. Things that are smaller than atoms, so they're called subatomic particles. And so atoms are indeed the smallest piece. They're the smallest piece of copper you can get. They're the smallest piece of. Are they the smallest piece of water you can get? Would atoms be the smallest piece of water? Yeah, when we look at water, it's a little bit different. So let's go back and take a look at water. So here's the particulate level. Here we have macroscopic we see with our eyes. When we try to visualize what's happening, obviously we can't see this with our eyes, but with sophisticated instruments we can see individual water molecules. And so is the smallest piece of water would have to have 2 hydrogens and 1 oxygen. It's H2O. And so if we tried to break this apart, would it still be water? If we broke the hydrogens from the... No, it wouldn't be. And so the smallest piece of water we can have is called the molecule. What about the smallest piece of gold? What do you think? A gold molecule or a gold atom? It would be an atom. Yeah. That would be the smallest. So, back to this. Pretty much everybody believes in atoms. Why? Because see it, the amount of evidence for the existence of atoms is overwhelming. I mean, so many images, so many X-rays. I mean, water even. Did I show you the crystals? I mean, did I show you the X-rays? Let me show you that. This is, do you know what this is? This is copper. This is a tiny, tiny crystal of copper. But we can make a smaller crystal. We can just break this in half. That would be a smaller crystal. And we can break it in a quarter. We can just keep breaking it down until we're left with a single atom. So this is copper. Oh, we can make it bigger or smaller. There's no real fixed boundary. Let's deal with my water. So what they do with water is it's too hard to take a picture of liquid water. You know why? All the liquid water molecules are moving all about. They aren't staying in one place. If you want to get a picture of a water molecule, you got to make sure they stay in one place because it's a very slow snapshot, right? With shining X-rays on it. You got to stay still for a long time. I did these X-ray measurements, and you had to make sure that it stays still for, it took 12 hours to generate the image. And so the only way you could generate the image is you got to freeze it down. Fortunately, mine was already frozen. Mine was already solid, so I didn't have to worry about it. But this is ice, so you get the water molecules to stay put, and then you hit it with X-rays, and then you can see where all the water molecules are and then measure the water molecules individually. Although this is not what the water molecules look like. They model it, using ball and stick models like this here. So this X-ray structure of water. This is another molecule. The smallest piece of this would be a single molecule. Because if we try to break this, let's say in half or in a quarter, it's no longer going to behave like this at all. And so these crystal structures are very, very useful. They show us how things are bonded together. This is a gigantic molecule called a protein. There are different ways we represent it. Since there's so many, if you did a ball and stick, it kind of gets confusing. This is space filling here. This is a wire diagram where they just show the sticks and omit the balls. This is a ribbon diagram, so you can kind of, sometimes it's hard to follow because it's so jagged. But if you kind of look at the structure here, it forms ribbons. Ribbons, which are these helical structures, and then sheets, which are these straight structures like this. You get helical and sheet structures like this. That's a backbone. Same thing with proteins. They try to cool them down and then grow crystals. These are crystal structures as well. This is usually what you get out of the computer. It looks something like this, and then you space fill it like this, or wire frame it like that. Get a better look at it. This is just a wire structure representation. This is not just one molecule. This looks like more than one molecule here. Myoglobin. This is two molecules here. They're showing just how two molecules interact with each other. One molecule is the drug, the other is the enzyme. The enzyme is a biological molecule here. So this is the drug here that's interacting with the biomolecule. So nowadays we see, everybody's seen lots of atoms in science, and so it's not typically a dispute. But think about in the 1800s. In the 1800s, the critics were a lot more empowered because there wasn't all this overwhelming evidence for atoms, and so Dalton had to argue that for the existence of atoms without ever having seen any atoms. We're lucky because we can see the atoms using instruments. We can see the atoms. Not only can we see the atoms, we can manipulate the atoms, and smash the atoms, and do other things with the atoms. But in Dalton's time, think, what would you have given as evidence for the existence of atoms? And in fact, why did he come up with such a crazy idea that, you would think things are infinitely divisible because that's what we see. We take a piece of copper and we can just keep breaking it smaller and smaller, and so it seems like there should be no end. But there is an end, and the end comes at about 100 picometers, 100 to 600 picometers. This is the smallest piece you can have because that would correspond to a single atom. And so we need some kind of evidence in support of this that doesn't rely on these sophisticated instruments. And so we got to think, what comes first? The theory, the hypothesis, the law, the pattern, the observations, what comes first? How did Dalton come up with this idea? Well, he must have had some justification for it. He must have been trying to explain some kind of pattern or some kind of law, because he hypothesized the existence of atoms. So why? It's not like it's some random thought all of a sudden. Okay, atoms. I don't know why, but it just came to me. Atoms must exist. Right? It wasn't like that. It followed the scientific method. And so what we got to do is we got to look back and see what what even gave Dalton the idea that atoms do indeed exist. And I mentioned this yesterday, but it was very quick. I don't know if anybody caught it. Anybody remember? How about, anybody remember the joke about the two people that went up to the bar? Yeah, one ordered H2O. What was that about? H2O versus H2O2. Maybe it didn't make any sense at all, but if it doesn't make any sense at all, what you should do is, like I said, when I started at UCLA, I totally changed the way I studied. Up until that point, I always highlighted the book. I had a highlighter, highlighted the book, I annotated the book, I did everything with the book. At UCLA, I gave up. I put the book down and then just did everything in my note. So rather than highlighting something in the book, I just wrote it in my notes. So if I saw an important sentence or an important passage, I'd make sure I had that in my notes. So that was the one sentence I'd focus on. But another thing I do is this. If that joke seemed pointless, then I would make a note. Pointless joke. Don't bother studying it. Right? Or if there was a point, I'd say, okay, what was the take-home point of that joke? Was there any take-home point? If there's no take-home point, then I could actually erase that from my notes and I'll be good. But was there a point to that? What?
Like depending on the number of atoms you have, the molecule can change to something different. So instead of like H2O, you had H2O2, the hydrogen peroxide, which is the
Yeah, that's absolutely right. Hydrogen peroxide, H2O2. So that was one point. H2O versus H2O2. These have different compositions, they're going to have different properties. But there was one other thing that was there. What about H2O 1.2? Would you expect H2O 1.2 to be maybe, let's say, 20% toxic, 80% less toxic than, because it's about 80% of, it's only 20% of the way to hydrogen peroxide. Water is critical for life. Hydrogen peroxide is deadly for life. And so since this is 20% of the way, maybe it has a 20% of toxicity compared to something like this, H2O 1.8. If I had H2O 1.8, that's 80% of the way to hydrogen peroxide, which is H2O2, which means it's going to have 80% of the toxicity of hydrogen peroxide. Maybe not a full 100% of the toxicity, because it's not quite at H2O2. Is that reasonable thinking? Why H2O2? Why not? Okay, I guess it wouldn't work with a joke, but if the person ordered in other words, there was something else about this, and that is, do you think H2O 1.2 exists? No, because can I get 2/10? I just want to slice 2/10 of the atom off. Just give me 2/10. You keep 8/10 of it. Of the atom. Is that going to work? No. So compounds like this, these don't happen. This is what we call the law of constant composition, the law of multiple proportions. Where did the law of multiple proportions come from? Now I know I went through this too fast, probably. But I mentioned Dalton yesterday, Dalton's atomic theory. And so basically this. Dalton's atomic theory came from observations. Now, what observations led him to think that atoms must exist? And what observations led him to think were these? This is an example of what we call a chemical property, combustion. And results in a chemical change. So here they're burning phosphorus. When they burn phosphorus, take a look at what happened to the air. Do we still have the same amount of air? Do we still have phosphorus there? No, we'd have some kind of ash in there, not phosphorus. And so we do an experiment like this, and one thing is, it looks like we lost a lot of air, right? If we lost a lot of air, then is air weightless, or does air have weight to it? Air has weight to it. You know, air has mass. I mean, you can feel it. And so this looks like we lost mass, doesn't it? If we lose some air, it's going to weigh less. It's like, you know, have you ever used those compressed air dusters? You know, when it goes empty, it gets really light compared to when it's full. You can tell. And so this is kind of empty, so this has got to be lighter than this, right, if we were to weigh it, I think. But it turns out that, interestingly enough, they weigh the same. And so before and after, these two things weigh exactly the same. Okay, that's interesting. Maybe this is a one-off type of deal. Maybe it's a one-off type of deal. It's a rare occurrence. But they took something completely different, like mercury. You take something completely different, like mercury, and burn it. And you know what happens? The weight before burning it and the weight after burning it are the same. And the same thing, you take a wood log, you burn it. Well, the wood log is going to turn into ash. It's going to get lighter, but you're going to generate a lot of gas. That gas you can capture and weigh. And you know what happens? The weight before burning and the weight after burning are the same. The same thing with methane. Do you know 1 pound of methane? I calculated this before and I can't remember it. I think 1 pound of methane produces 4 pounds of water when you burn it. And I think about 3 pounds of carbon dioxide. I got to double check. We're going to do the calculation anyway, so if my numbers are off, we'll soon figure it out. I should do it in my head right now, but I don't want to spend the time. But the point is, there's a repeating pattern here. The repeating pattern is this. Whenever you do some kind of chemical change like this combustion, the weight before and the weight after are the same. Therefore, we can call that a law. A law, well, obviously we're going to try to find a violation of the law. And so we're going to try burning everything we can burn and see if we can find a violation. If we find a violation of the law is no longer valid. But there's no violation of that law that we can find. And so we give this law a name. You know the name of this law? The name of this law is the law of conservation of mass, or the law of I guess conservation of mass, or what's the other name for this? Mass is conserved law. In other words, the mass doesn't change before and after something drastic like this happens. And so what does that mean about the atoms? Did we lose any atoms, or did we gain any atoms in the process? No. And so that throws out phlogiston. You know, that phlogiston is this stuff, this invisible stuff disappears. If it disappears, then, well, we didn't detect it disappearing in the mass, right? And so that debunks phlogiston. But it also brings up the point, because, you know, the stuff before and after look totally different. So when I burn natural gas before, and then after, do you know what happens when I burn this? It forms carbon dioxide and water, which have totally different properties than methane and oxygen. When I burn phosphorus with oxygen, you know, I get phosphorus oxides, which have totally different properties. And so why Dalton thought of atoms is he thought these atoms are just rearranged in these chemical reactions. And so the carbon of methane is made up of carbon and hydrogen atoms. This is methane here. So the black one is carbon and the white ones are hydrogen. These are three. Here's a drawing of it trying to show its structure. Well, we're very interested in the three-dimensional structure of these molecules, whatever we're looking at. We're interested in the three-dimensional structure. So this is ball and stick here, these two. This is space filling. This is space filling overlaying the ball and stick. And again, when you probe the surface of this, when we probe the surface of the molecule, it's not like this. You know, you don't hit a hard surface. You know, it's a soft. This is more spongy. Eventually, it'll feel hard because the repulsion takes place, but we'll talk about that later. Anyway, so when methane's burned in air, then all the atoms are rearranged. They're going to form things like CO2 and water. CO2 and water. So it forms. However, you got to be careful because, let's say, if you don't have enough air, do you know what you can form if you don't have enough air? And this is why you got to be careful. A lot of people have methane or natural gas water heaters. A lot of people have natural gas stoves, natural gas ovens. And if those ovens, stoves, and water heaters aren't tuned properly, that is, there's not enough air getting in there. Oh, I forgot to take the break. Then we have the risk of generating this. You know, normally carbon dioxide forms, and that's okay, but because you know, a little bit of carbon dioxide won't kill us. However, a little bit of this will kill us. What's that? Carbon monoxide. So a lot of houses have carbon monoxide detectors. But what about this? You know, if matter were infinitely divisible, if matter didn't occur as atoms, you know, then maybe I could form something half as toxic as carbon monoxide, CO 1.5. You just put 1.5 oxygen atoms on the carbon. Would that be half as toxic? Do you expect carbon CO 1.5 to exist? And so, so in other words, so based on these observations, if matter was indeed infinitely divisible, then we should be able to put any amount of oxygen we want, any amount, because we can divide it infinitely, small or infinitely big, and anything in between, right? And so that's the evidence that, and then theory should do two things. Let me finish with this before we go on a break. Theory should give a fundamental description. The fundamental description of the atoms are rearranged in these combustion reactions, and it should be able to predict something. What did the atomic theory predict? It predicted a new law. And do you know what that new law was that it predicted? The new law that it predicted was the law of multiple proportions. This is a law I've been talking about here. It wasn't really sorted out. Nobody really proposed it up until this point, but once Dalton's atomic theory came about, then it made total sense that these atoms can only combine in simple whole number ratios. And we can't have any fraction up here. Does that make sense? And so with that, you know, he had gained a lot of scientists in his camp versus the infinitely divisible camp. Even though still, you know, you might not think that's the strongest argument there is for the existence of atoms, which it isn't, and so it's just very impressive what he did, but it was enough to compel the theory to live and last. All right, let's take a break for 10 and then we'll start again.